Welcome to the channel, students. We have started with the second chapter of first unit electrostats, that is electrostatic potential and capacitance. In this particular chapter, basically we will be trying to establish the interaction between already studied topics force and field with a new topic of electrostatic potential. Yes, in this chapter we will basically start with the study of potential followed by the study of potential energy, and we would be connecting them to a very wonderful instrument used for storing charges, that is capacitors or condensers. So let's begin with the chapter. Today we will concentrate on this word potential. I would like you to understand that it is basically going to be study of space. Potential is basically a number associated with space. In order to understand what I am trying to say, let us consider a situation. A charge, positive charge, capital Q, source charge, and you know that the field or the space around the source charge is modified and now it will have some electric field. If I put another charge plus Q, it's of same polarity or nature as of the source charge at any point A at some distance from the source charge. What do you think? Plus Q will experience, yes, it will experience force of repulsion. You can even call it electrostatic force. And what will be the direction? Yes, it will be directed away from the source charge, or the source charge will try to push the positive charge away from itself. Now, if I want to bring this charge plus Q close to the positive charge or the source charge, what should I do? I have to apply external force. And what should be the direction? External force, I will represent it by F EXT, and its direction should be opposite to F repulsion and it should be towards plus Q. Now this F external tries to shift the charge plus Q from position A to position B. Let us say for our convenience it shifts it through small distance dr. Now if there is some force acting on the charge and there is some distance involved, don't you think that some work is done? Yes, the work is done in shifting the charge from A to B. What is the work done? It is, total work done is integral A to B, the applied force which is F external dot the distance through which the charge is moved. Why have we taken integral? Because when we move it through small distance dr, it is small work done. And we want to generalize the situation to get the total work done for each and every involved point. We don't want to miss any of the points from A to Q. We want to consider the work done for each and every small dot point over there continuously. So we are integrating it. F external is the applied force into the distance through which the charge has moved. This is of course, suppose if I instead of F external, I use F repulsion. It is, if I put F external in place of F external, I put F repulsion dot dr, then here there will be negative sign. Why? Because F external and F repulsion, they are in opposite directions, and magnitude wise F external we have taken equal to F repulsion, or F, in better situation we should call it F electrostatic, because it can be repulsive, it can be attractive, but basically it is electrostatic. Magnitude wise same. Why we have taken it of same magnitude? Yes, that thing will be clear when we will try to define potential. Remember, we haven't yet started with the topic potential. Presently, I'm trying to convey something which you already know, because these things are analogous to what you already studied when you were in class 11th and you were dealing with the concepts of gravitational field, gravitational potential energy. So, I told you that if a charge has to be moved closer against the repulsive force, we have to apply external force. And when there is some force, there is some distance, there is some work done. And that work done I denote by subscript AB, work done in moving the charge from A to B, which is continuous integral force into displacement. This is nothing new because you have already studied it for spring force, you have studied it for gravitational force, where you always took the force into displacement. So if I take it F repulsion, then the negative sign will come into play because F external and repulsive are in opposite directions. Now, if I talk about this work done, then what happens to the work which is done? If suppose this charge has shifted from this position to this position, A to B, what happens to this work done? You already know this work done is stored in the form of potential energy. You can call it as potential energy, and this potential energy we denote it as potential energy. This work done is stored in the form of potential energy, same way we dealt in the case of gravitational field. Now potential energy can be having the values UA, UB. UA is the potential energy which the charge is having at the point A. UB is the potential energy which the charge is having at the point B. Now if I talk about the potential energy difference, then of course the potential energy difference will be UB minus UA. Why I have taken UB minus UA, not UA minus UB is, you always know that as you bring the charge closer and closer to the source charge, you have to do more and more and more work. The work has to increase, or you can say you have to increase your external force in order to bring it more closer. The closer you want to bring, the more external force you have to apply, because the more repulsive force will be in the play. So when F external increases, work done increases. When work done increases, potential increases. So potential at the point B will be greater than that A. If I take any other point at random C here, then the potential at this point C will be still greater than the potential at the point B. So potential difference will be UB minus UA, which is potential energy at B minus potential energy at the point A. Now if I take this potential energy and divide it, suppose I take this potential energy and divide it by the charge which we are trying to shift. Work done per unit charge. What is this? Work done in shifting the charge. Work done in shifting the charge Q from A to B. This is nothing but potential. What will be the units? Work done will have the units of joules, and charge will have the units of coulombs. So the SI unit of potential will be, don't worry about the definitions. After studying and understanding the fundamental concepts, we will be defining them, and you will have enough time to note down the definitions. So it is, potential is nothing but, it is the work done in shifting the charge from point A to point B, or any 2 points in the electric field of source charge. So it is joules per coulomb. Now you must be wondering, what are these dots representing? I just want to tell you something. Suppose these dots represent some general points in space. Now what would you like to say? Is there any potential at this point? The answer will be no. Why? Because there is no source charge which can be seen in the vicinity of this point. If I take at random any other point, say this, is there any potential here? The answer would be no. The potential here? No. Why? Because there is no source charge here to produce electric field. When there is no electric field, there is no source charge, no electric field. No electric field, then there is no force. And when there is no force, then there is no work done. And if no work is done, then there is no concept of potential. If you are able to connect all these interactive terms in the form of a chain. Because we have already studied about force and fields in the previous chapter, we are in a, what you can say, sound mind and position to correlate them. Since there is no source charge, there is no electric field. No field, no electric force. If there is no electric force, no work is done and no electric potential is there. Now let us change the situation. If I put a source charge somewhere at the location A here, then will there be any potential here? Yes, there will be some potential. Why? Because at this point B, we will have some electric field, and the electric field will make us, what you can say, experience, will make us understand that the charge, if any charge is kept over here, it will experience some electric force. That force can be attractive or repulsive depending on the nature of these charges. If there is some repulsive force or attractive force, then there has to be some work done if it moves through some distance. And if work is done, it gets stored in the form of potential energy. And work done per charge gives you potential. So we can say that there will be some potential at the point B. And I call it some value, say VB. Will there be any potential at the point C? Yes, of course. There will be some potential at the value C also. And what would you like to comment about potential at B and C? Yes, potential at B will be greater than potential at C because it's a positive charge, and the closer you come to the source charge, the work done will increase, the F external factor will increase, and more energy is stored. But as you go on moving away from the source charge, the potential value goes on decreasing. Here you can say the value close to it will be big, and the value close or away from it will be small. The value of V is close to the charge is big and away from it is small. Why are we studying about potential? For the very obvious reason that its unit is joules per coulomb. Means what? Joules refers to energy per unit charge. Whenever there is some involvement of energy, it is a point of our interest because we all are trying to conserve energy, store energy, use energy, produce energy, and so many things. So whenever there is something called energy is involved, it requires our understanding. Suppose if I put it like this and I say, let us take an example, say any point here D. If I say the energy or the potential at this point is 100 joules per coulomb. If I say potential at the point D is 100 joules per coulomb, what do I mean practically? I mean, if I bring a guest charge, say a guest charge has come, let us say it is 2 coulombs. We got a guest charge. It has come and the value of the guest charge is 2 coulombs, and it has come and it wants to reside at the point D. Then what will be the potential at the point D? Yes, or you can say the potential at the point D will be, it's already given 100 joules per coulomb. Then what will be the energy which will be experienced by the source charge? Its energy will be the potential energy of the source charge at the point, or the the charge Q at the point D will be, energy is nothing but work done, and work done equal to VQ. So the value of V at that point is 100 joules per coulomb and the charge is 2 coulombs. What do we get? Coulombs get cancelled and you get 200 joules of work or energy. Got it? Suppose at this point the potential is 100 joules per coulomb, and if any guest charge, say 2 coulombs, comes and sits here, then it will have an energy of 200 joules. Interesting, isn't it? Now we have studied so many things. You would like to note down few concepts and definitions. So let's move on to the definition of potential. You remember, I've always told you that in physics it is very difficult if you try to mug up some definitions. We need to understand, conceptualize, and then we can always put them or frame them into words. So can you compare these two situations? I believe you are familiar with one of these situations you studied in 11th, where you are considering MGH, the gravitational potential energy. When you have seen the difference in the heights between A and B and a person moving up, how the potential energy is gained. Now you apply the same concept for electrostatic potential energy. How the difference in potential leads to picking up of potential energy. Just concentrate and see how delta V, difference in potential, gives rise to the concept of potential energy. Yes? Okay, now have a look at this diagram also. It will also help you to give a fresh definition of electrostatic potential, which talks about electrostatic potential in terms of electrostatic pressure. Fine. Now we can write the definitions. We can put them in words. Okay. So from the figures you have interpreted the first definition as electric pressure per charge, isn't it? The other way to define the same thing is, it is the work required to be done by the external force. Yes, this is something which we have already seen. After understanding the concept, we are defining it as the work required to be done by the external force in moving a charge from one point to another. And here I have highlighted this thing without acceleration. I have written it in a highlighted manner. Without acceleration implies that you have already taken F external magnitude wise is equal to F electrostatic. Magnitude wise they are same, direction wise they are opposite. So net force is 0. The charge moves with constant velocity. So it is the work required to be done. Who is doing the work? By the external force. On whom? A charge. In what? In shifting the charge from one point to another. How? Without acceleration. Where? In the electric field of any charge configuration. You can have a point charge, single point charge, source charge. You can have multiple charges. You can have spherical charge configuration or a sheet or line charge, whatever. So it is the work required to be done by the external force in moving a charge from one point to another without acceleration in the electric field of any charge configuration. Mathematically, we have already seen it is defined as the work done per unit charge. Work done in shifting the charge from A to B. If I look at the same diagram again, source charge, point A, point B, we are bringing plus Q from point, we should write it A and B here. The charge is being brought from A to B. We are shifting the charge by applying external force which is equal to the repulsive force. Repulsive force is in the direction pushing it away, and you are trying to bring this in by using external force. So work done in bringing it, work done AB upon charge Q which you are bringing. This gives rise to the concept of potential. It is the work done in shifting the charge from A to B. Difference in potential difference. It is the potential difference between the points B and A. It can be any 2 points in the electric field. You can even write it as potential energy at B minus potential energy at A divided by the charge which is getting shifted and not the source charge. Remember, here this charge is the charge which is being shifted or the charge which is moving, not the source charge. So this is giving rise to V. If suppose your point A, initial point from which you are bringing the charge, is at infinity. Suppose it is somewhere at infinity, far off distance, where, what is infinity? It is considered to be that distance where the effect due to the source charge is negligible, or the source charge is having, what you can say, the electric field value over that point is 0 also. So if the initial point, if suppose this point is somewhere at infinity, then at infinity the potential energy is 0 and you are bringing the charge from infinity to any point B in the field of the source charge. We can write this as work done from A to B, shifting the charge from A to B, now it becomes from infinity to B divided by charge Q. It is the potential difference between the points B and infinity. Potential at the point B and infinity. This is the potential difference, or you can say it is the potential value also. It can be defined also as the potential, can be defined as the work done in shifting the charge from infinity to some point in the electric field of source charge. You can even define it like this. Work done in shifting the charge from infinity to some point in the electric field of source charge. So ultimately we have arrived at this conclusion in the form of flow chart. Work done in shifting the charge from A to B. This work done gets converted to potential energy of the charge. When you do some work in shifting the charge from A to B, that work done is converted to potential energy. And when you remove the external force, suppose you remove the external force, F external is removed, then what happens to that charge? The moving charge, it now tries to move away from the source charge. And who gives it the energy, or from where it gets it from the kinetic energy. You can say work done gets converted to potential energy when you apply external force, and when you remove the external force, the stored potential energy is converted to kinetic energy, giving the charge a motion away from the source charge. I hope you got it. Thank you.